So welcome to another CPD seminar for structural engineers. Today we'll be talking about retaining walls, looking at the MBIE Module 6 and the New Zealand Building Code section B1 and the verification method number 4 that it provides. So primarily looking at concrete cantilever retaining walls, and we're following that procedure given in Appendix C of the verification method for B1 VM4, as well as the Earthquake Geotechnical Practice modules for earthquake-resistant retaining wall design. And yes, this is another seminar, and it's going to be asking the question, what the hell does this spreadsheet do? Because those familiar with Redco know we have lots of spreadsheets, and they're all very clever, but not quite clear as to what they're actually doing. So all of those with Redco spreadsheets will be, no doubt, fully informed about the engineering behind those spreadsheets. So the scope, just a reminder that I'm not a geotechnical engineer. I just use the soil properties provided by the geotechnical engineer and follow the recommendations provided in the Geotechnical Interpretive Report. So I'll be looking at the structural design primarily, and in this case we're looking at retaining walls. We're not going to be looking today at slope stability analysis or deep-seated rotational failure. Now these are the things you need to look at as well when designing retaining walls, but you should do that in consultation with your geotechnical engineer. So the possible modes of failure as given in the MBIE guidelines. Well, we'll be looking at wall stem structural failure over here. Just actually the root of the concrete wall fails in bending. We're also looking at foundation bearing failure, so the ground just can't take any more. We'll be looking at the sliding of the wall, so your earth is pushing it away from itself. What we won't be looking at, but what you need to look at, is deep-seated rotational failure, which your geotechnical engineer should be able to help you with. So here is a glimpse at the New Zealand Building Code section B1 on structure, and at the back of it you'll find verification method B1 VM4, and that's for foundations. We'll also be looking at the Earthquake Geotechnical Practice guidelines from the Ministry of Business, Innovation and Environment, also known as MBIE or MB. And they've published a number of modules, in this case 6, which are all worth reading. You can download them from the MBIE website, or just Google the titles that you'll require. So search for Geotechnical Engineering Practice modules, and you can download these documents. And they are worth reading because it goes into earthquake design of foundations, retaining walls, piles, and so on. Today we're looking at module 6. And the real way to understand it is actually to do and write out the examples. So MBIE highlight 6 cases for retaining walls. And case 1 is where you have a retaining wall that's integral to the building, so it's part of the building built into it. You've got a second case where the retaining wall is supporting the building. Case 3, which is our example today, it's a retaining wall, but it's supporting the foundation for the building. So the building isn't actually sitting on the retaining wall, it's basically surcharging it. So the retaining wall is dependent on the ground conditions, and the building is dependent on the retaining wall for its stability. Case 4 looks at a wall that's protecting an upward slope near to a building. Case 5 is looking at facilitating access or service to buildings. So perhaps you've got a path, a driveway or a road next to maybe your building's over here, but it's far enough away not to be influenced by it. But that support will be provided by your retaining wall to that road or driveway. And finally, case 6, these are all the other situations where you've pretty much got standalone retaining walls. So a reminder of the soil types we'll be looking at. You have cohesive and cohesion-less soils. Let's begin with cohesive soils. And you look at short-term analysis using the undrained shear strength and total stresses. Long-term analysis is using effective strength and using the strength parameters C' and phi' for the cohesive soil, usually clays or silts. On the other hand, cohesionless, and we're looking at effective stresses and using C' and phi' for the long-term analysis. So you don't tend to look at the short-term analysis in there. Water plays a big part in the design of your foundations, and it's critical to the behavior of the soil, and it determines the strength of shear strength parameters. And if water is present in the soil, the applied loads can be carried by the pore water pressures, at least in the short term. So for granular soils above the water table, pore water pressures dissipate almost immediately as the water drains away, and the loads are effectively carried by the soil structure. If you're looking at fine-grained soils like silts and clays, these are not so free draining, and pore water pressures take much longer to dissipate, so you need to take them into account in the design. So remember this from a previous seminar, these are the old Mohs circles of stress. And in drained conditions, we're looking at long-term loading, and we're assuming that the pore water pressures have dissipated, and we're looking at design based on effective stress and the parameters phi' and C'. If you're looking at undrained conditions, then our angle of shearing resistance is often 0, and you're looking at short-term loading, looking at pore water pressures to be present, and the design is carried out based on the undrained parameters of phi and S. So there are a number of ways of calculating the earth pressures on the retaining wall, and this is probably the simplest, presented by ranking. And so you have the coefficient for active pressure, Ka, given by the simple formula here. Similarly, you've got Kp, which is pretty much the inverse of Ka, and where you've got the coefficient of pressure at rest, it's an even simpler formula given there. Now, for the active pressure to be mobilized, we're assuming that the wall is flexible and that the top of the wall will move. If the top of the wall doesn't move, or assuming that the wall is rigid, the pressure on the wall is governed by the earth pressure at rest coefficient. Now, there's lots of assumptions made for the ranking earth pressure parameters. Here they are, I won't read them all out, but basically you're assuming that the wall is vertical and the ground is horizontal, and the backfill is also horizontal. A slightly more complicated one, because things are not always as simple as shown in the Rankine formula. We've got some earth pressure parameters provided by Coulomb. So your slope of your ground behind the wall can be represented by beta, the slope of the ground in front of the wall by beta dash. And even the wall itself can be sloped by an angle alpha. So this makes life a lot more complicated. And to get that, we use these formula here. So the active pressure coefficient, Ka, is given by this formula. And that takes into account the angle of the ground and the angle of the back of the wall. Similarly, you've got the passive pressure coefficient, Kp. Now, that is all for static analysis. For dynamic analysis, chaps called Monarbi, Okabe, and Kapila calculated some graphs for the coefficient of earth pressure for dynamic conditions, i.e. for earthquake. And there's a whole series of tables or charts published, and you can find those in the back of the Build It Right Canterbury supplementary guidance, which is available for download. and they go through each value or a range of values for phi, delta, and beta, as well as your backslope I. Well, in our case, our backslope is 0, and we've got a 30 degrees, and we've got a delta of 0 and a beta of 0. So our KH, which you'll come across in the example, we've got as 0.2, so we can read that off there. Now, old school engineers tend to like graphs, but the more modern ones and computers do like equations. And here is the equation, and what an equation it is. And this takes into account the parameter, which is in this case theta. And the theta takes into account this KH factor here. And so it pops out as 0.471, which we'll see again later. And here's some more graphs, and you can tell they're all by the state of the scanning. These are from an American standard, but for some odd reason, the MBIE decided to use them in their worked example. So they take their active and passive pressure in the static case from these charts or these diagrams. They are quite difficult to read, as you can see, and they're quite difficult to interpret. There's also some fiddle factors you've got to use in there. A couple of parameters you need to know about in the worked examples. The first one is the topographic application factor, a topo. And this is from the MBIE guidelines. And your KH factor, which we've mentioned before, is the product of the acceleration and the A topo factor multiplied by the WD. So what's that WD? Well, we'll come across that in the next slide. But generally, they've given a nice table in the guidance, and you can use one of these values. For slopes less than 15 degrees, A topo works out as 1 anyway. If you're on a cliff edge, then you're looking at a 1.2 amplification factor. The wall displacement factor, WD, is given in table 5.2 in the guidelines. And so that tends to refer to the type of situation you're in. So remember our 6 cases, we've got 6 values of WD. Generally, the WD is taken as 1 for the serviceability limit state. The tables in the 5.2 are given for the ultimate limit state. Other international practice has shown that the coefficient somewhere between 0.33 and 0.5 of the peak ground acceleration tends to be about right. So here's our Redco Excel spreadsheet, and so the Redco boys will be familiar with this, and no doubt will have written copious amounts of calculations and validation files for these. And again, this does an awful lot of things. First, it works out what the loading is, and then it tries to calculate the reinforcement, whether it's a masonry wall or a concrete wall. And again, that's an awful lot of things to do for a spreadsheet. And so to our example, this is the example 2 in the MBIE module 6. And it's a concrete cantilever retaining wall, and it's 2.5 meters high. It's got a surcharge of little w on the top, and it's got a load on the back of the wall because of the amount of earth on the back of the wall holding the retaining wall down. The passive pressure acts at an angle, and so that will end up being resolved into horizontal and vertical components. And similarly, the component of the passive pressure is actually acting at an angle. We take moments about the pivot point here at the toe of the retaining wall. So here is the example. Let's keep these figures in mind as we go through the example. So here's your figures on your left, and here's the Mathcad on the right. So this is the Mathcad for the concrete cantilever retaining wall, and this is straight out of the module 6 of the earthquake resistant retaining wall design. So modes of failure, as we've discussed before, you can look at wall stem failure, foundation bearing failure, sliding failure of the wall. So that's the foundations moving. The fourth mode of failure we won't look at today, but they should be considered by your geotechnical engineer. So here are the diagrams for those modes of failure. So your base of your stem is failing. You've got too much moment in the base of your concrete wall for the concrete capacity to carry it. The next two are about geotechnics. So the ground underneath can't take any more load and basically moves and yields under the pressure. Alternatively, they can slide out of the way. So you're pushing on the back of a wall, it just might move out of the way. And finally, your deep-seated rotational failure. You have a guess at which of the circles that will cause the failure. So you're looking at the lower limit for that. As I keep reminding you, these are just some of the models that can be used to analyze your retaining wall. And remember, all models are wrong, just some of them are useful. And that's probably doubly so for geotechnics and even more so in New Zealand. So we put in our wall properties, so the length of the base, width of the stem, and so on, how long the toe is and the heel is. That's just straight out of the example, and derive the width of the footing and the weight of the footing from the parameters given above. We assume from soil parameters that our unit weight of soil, gamma S, is 18, our angle of shearing resistance is 30, and our inclination is 0, of course. And we've got a cohesion, effective cohesion for the drained condition of 0. And from that very old graph, that's the nav effect graph that's provided in the example, you take the coefficient of active earth pressure, KAH, as 0.3, and the coefficient of passive earth pressure as 5.5. The 5.5 derives from the figure 0.65 multiplied by the 0.85. That's the fiddle factor you'll find in the table next to the graph. Yes, very complicated. And for the earthquake case, we're looking at undrained short term, and we take our angle of shearing resistance as 0 and our cohesion CU as 50 kPa. Our imposed loading on the surface, and W, in this case we've called it Q, as 5, but in cases where it's stabilizing, we've put a smaller factor in there. Now looking on to the seismic parameters. Now this example is based in Christchurch, and most of the examples based in that MBIE guidance are taken from Christchurch. So it's assumed it's Class C soils, and you're looking at a 500-year return period. So from the example, we've given that the Amax is a 0.4 of the G, acceleration due to gravity. Topographic amplification is 1, so we're not near a cliff edge or a ridge top. Our wall displacement factor is 0.5 because of the scenario we're looking at. So that equates to a horizontal acceleration of 0.2 G. Now we're ignoring the vertical acceleration for simplicity. There are nearly always vertical components to your earthquake action, but for most of our designs, we tend to ignore them because they're usually quite small. So because we've adopted a WD of 0.5, we're assuming that the wall and the retained ground are likely to yield. And that because of that, you're going to get permanent displacement behind the wall during the design earthquake event. The wall must be sufficiently robust or ductile to accommodate that movement, and some settlement is expected following the earthquake. So that's the model we're using to work out what the loading is on our cantilever retaining wall. And we'll keep this to the side so it's a reminder of what's going on. Gravity case will usually be the dominant load case, not always, depending on where you are, but we do need to check against the seismic load case. For the simplified procedure, we look at the middle third rule, and it's much easier if you do apply the middle third rule. Otherwise, it's a very complicated analysis. And we've got to take into account the applied horizontal loads and the soil pressures. So here are our strength reduction factors that we'll be looking at, or resistance factors. So when we're looking at bearing in the gravity case, we've taken this from the NZBC VM4, and we're looking at a load resistance, or a resistance factor of 0.5. And against sliding, we can use 0.8. And for passive pressures, we can use 0.5. Where we're stabilizing, we apply a 0.9 factor. Where it's destabilizing, we apply a 1.2 factor. Okay, so first we need to check the middle third rule. And we do this by taking moments about the toe. That's that point there. And so we work out what the active thrust is. So our PA, there's our PA, and it's worked out as the coefficient of active earth pressure multiplied by the soil unit weight multiplied by the height of the retained soil squared. And we take that as half of it because it's a triangular distribution. There is, of course, a vertical and a horizontal component to these because the passive active earth pressure is acting at an angle. So our active soil thrust, the horizontal component is 20 kilonewtons per meter, while the vertical one is 11. So that's for the soil. Let's look at the result of the surcharge. The surcharge is on the top of the retaining wall, and again, that effectively is at an angle. So we have a vertical component because of that angle of 2.2 and a horizontal component of 3.8. We can also allow for a surcharge above the heel. That's this thing here marked as W on the diagram, but it's worked out as PQ here, of 3 kilonewtons per meter. Then we work out the moment from the horizontal active pressure, and that by taking the forces and multiplying by the lever arms, and we get out 31 kilonewtons. The moment from the vertical active pressures, the vertical components, which potentially can be restoring, works out as 25 kilonewtons. That really should be kilonewton meters per meter. And the moment from the surcharge soil above the heel, and again that's restoring, is 4.05. So the full restoring moment from the self-weight of the soil, from the self-weight of the wall, and works out, if you multiply the weights by the lever arms by the stabilizing factor, in this case 0.9, we work out as a restoring moment of 74 kilonewton meters per meter. The net moment about the toe, that's neglecting this passive pressure, works out as 72.9 kilonewton meters per meter. So your factored vertical loading on the footing works out again. You multiply the weights by a stabilizing factor and add it up with your passive resistance, active pressure, and you get your 79 kilonewtons per meter. So what we do is we work out where it is applied. So we take our moment and divide it by the vertical component as basically the resultant, and we find out where the middle third is. So it's somewhere between L/3 and 2/3 of L. So our applied position, so the line of action is in the middle third because it lies between 1/3 L and 2/3 L. That's okay. If it doesn't, I suggest you adjust the dimensions of the wall to suit. So then we look at the bearing capacity in the long term, so the drained bearing capacity. So our effective footing width we've worked out from above. We've also got our ultimate vertical load from above as well, and our ultimate horizontal load, again, we've worked out from above. As we've said, the ground slope in front of the footing is 0 and the tilt of the footing is 0. Our soil cohesion is 0 and our effective angle of shearing resistance is 30. We're taking the adhesion under the footing, we're multiplying it by 1. There are different factors you can use there, but in this case we're multiplying it by 1. So here are the bearing capacity factors, and again they're given in B1 VM4. Now you can use the graphs given in there, or you can use the formula given in there, but if you use the formula, spot the errors. These numbers, these equations given in the B1 VM4 are not quite right. So in our case, the bearing capacity factors NQ, NC, and N gamma work out as 18.4, 30.1, and 22.4. B1 VM4 also provides figures for our shape factors and our depth factors. Those work out at slightly above 1. And the load inclination factors are also given in B1 VM4, and they work out as the 0.3, 0.1, and 0.278. Because our ground is flat, our base is flat and horizontal, our ground inclination factors come out as all 1. Now, when you multiply all those figures above, you get the ultimate bearing strength given by the formula, again taken from B1 VM4. So our design bearing capacity is 78.3, and in our case our factor of safety against bearing works out as VU star over the VU. So our bearing capacity is actually smaller than the applied load. So, sorry, the applied load is bigger than our capacity. And to change that, we can alter the width of the footing to increase the area for the bearing capacity. However, what I've done there is use the parameters given in B1 VM4. I've also got another calculation which is taking it straight from the module 6 of MB, and they use slightly different parameters. They use parameters for the load inclination factors given here, and I think that's come from a formula by Vesek. And the load inclination factors end up slightly larger, so your bearing capacity is also slightly larger. So your design bearing capacity works out as 84.1 kilonewtons per meter, which gives our factor of safety in bearing as slightly over 1. How convenient. So we move on to the wall sliding. It's our third case we're considering today. And for wall sliding, we factor down the self-weight components because they're stabilizing and apply a factor of 0.9. The vertical component of active thrust is not factored, it's just 1 as before. And the vertical component of the passive resistance is also not factored because in fact it's destabilizing in this context. So let's check the wall sliding on the base of the footing. So we work out what the weight of soil trapped under the footing is. We've taken our interface friction angle for passive pressure as 20 degrees. We've got our passive resistance PP, that's that thing down here. That's 10. There's a horizontal and vertical component of that because it's at an angle. So our horizontal component is 9.4 and our vertical is 3.4. We can work out what the friction under the footing is as 47 and the factored ultimate resistance as 42. So our factor of safety works out as a 1.16, so the applied load is slightly smaller than the capacity. So the wall bending strength, this is again in the gravity case. So the wall might fail in bending down here, when the moment is at the maximum at the base of the cantilever wall. So you work out what the bending moment is in the stem. Now, for some reason, the example has moved on to a different way of working out what the active pressure is, and it's using the MO equations. So the coefficient of active earth pressure applied to the back of the wall is that large formula we've given before. And from that, you can work out what the active thrust of the soil is. And the horizontal component you need to know, because we're looking at the wall, not the base. And then we take the horizontal component of the active thrust due to the surcharge load. And then we calculate the ultimate bending moment in the stem. You take the horizontal forces and multiply it by the lever arms, and you get a 31.25 kilonewton meters per meter. And we'll go on then separately to calculate the capacity of the wall itself in terms of the concrete section capacity. That's in the next example. For now, we'll go on with the foundation bearing because we're still sticking with the MBIE example. So we need to check it in the earthquake case. And so we use a different formula, and we use our cohesion as the SU value, our undrained shear strength, and we're taking a KP, a passive coefficient of earth resistance, of 1, which is rather conservative, but it's safe. Again, we check the middle third rule, and then when our surcharge is actually stabilizing, we're using a 3 kPa. For the factored surcharge case, where it's destabilizing, we're taking an earthquake load case in this case, so we've got a reduced live load for our surcharge. Take again, our seismic coefficient is 0.2. Now our resistance factors are all scaled down to 1 because it's an earthquake case. From the Mononobe, Okabe, and Capilla's earth pressure coefficients, we can calculate that the active earth pressure coefficient, KAE, is the 0.471, as we've seen before from this very large equation. And that's popping in this value theta. And you get the theta to take into account the acceleration due to gravity of the earthquake load. From that, you can calculate the active thrust due to the soil, the active thrust due to the surcharge, and then the surcharge above the heel, which is potentially restoring. What we need to do then, because it's the dynamic load, we need to work out what the inertia is of these wall structural elements located behind the heel. So the lump of earth behind the heel is treated as part of the wall, and they're added as follows. So the inertia from the foot works out 2.2, and then from the key and the stem and the soil and so on. From that, you have the moment on the horizontal components. As you take your horizontal values and multiply by the lever arms, and you get out 31.179 kilonewton meters per meter. The moment from the vertical components works out as 39, and the moments from the surcharge above the heel works out as 4.05 kilonewton meters. So the total moment from inertial forces works out as 17.4. So the restoring moment from the self-weight of the wall and the soil above the heel is calculated again by taking the weights and multiplying by the lever arms. You need to look at this diagram on the left to work it out, and that pops out as 82.5 kilonewton meters per meter. You do the summation and you work out the net moment. And so the resultant force has an arm somewhere between 1/3 and 2/3 of the width. So we're in the middle third. If we're not in the middle third, you need to move the dimensions. The next thing to look at in the earthquake case is the bearing capacity. So this is again short-term and undrained. So we've gone through the soil parameters before. We've worked out the loading before, vertical and horizontal. And we're using again adhesion under that footing of 1 CU, which works out as 50 kPa. And we work out our bearing capacity factors again. Now, bear in mind the bearing capacity factors differ depending on when you're looking at undrained or drained situations. So B1 VM4 gives you an NC value of 5.14. And then you can easily derive the NQ and N gamma either by looking at the graphs or by popping them into the equations given in B1 VM4. Similarly with the shape factors and the depth factors that we've seen before. The load inclination factors are different this time because you've got slightly different loads. The load inclination factors remain as 1, and so we get an ultimate bearing strength in this case of 232 kPa. And so our factor of safety against bearing failure is over 4. So we can see that our seismic load case is not the governing case. Now look at wall sliding in the earthquake case. So we're taking our coefficient of passive earth pressure as 1, which is again quite conservative, but it's at least safe. We work out what our passive resistance is, and it's 21 in this case. And our sliding resistance works out as 104 kilonewtons per meter. So our factor of safety in sliding is over 2. So we're happy. And again, earthquake case is not the dominant case. So looking at the wall stem bending strength, so this is again the bottom of the wall, and it's about the structural failure of the wall. And you're looking at the earthquake case. So we take the interface friction as 0. We work out the coefficient of active earth pressure that we worked out before, bring that down. Active thrust from the soil is 26.5. Active thrust from the surcharge is 4.7. And the ultimate bending moment in the stem works out as 31 kilonewton meters per meter. And that you can then use to design the concrete wall. So this is the Mathcad for the concrete combined retaining wall and boundary wall design. So this is subject not just to earth pressure, it's also subject to wind loading. So this was a real world example. This is one I did a couple of years ago on a real project. So it's a concrete retaining wall, rather high. So your retained height is 1100 and your boundary wall height is 1800. So you need to calculate what the wind load is as well as what the earth load is as well. So some basic parameters of the wall, some concrete wall material properties. The loading, we've assumed surcharge loading on the backfill is only 2 because there's no traffic in there, it's only people. And it obviously acts on the soil level. The design wind speed, because we're looking at an IL1 structure, we're looking at a return period of 1 in 100 years. So our design wind speed is 37. And that gives you dynamic wind pressure of 0.84. Because our pressure coefficients are 1.2, we're going to work out with a wind pressure of 1, or just slightly over 1 kPa. So our combination factors for live loading on the back of the wall will be 0.3 in this case. We've got strength reduction factors as we've seen before as 0.5. If you're looking at long-term and loading, You can look at reduction factors of 0.4, again, for the line load as well as the surcharge load. Our soil pressure factor is going to be 1.5, but for earthquakes it will be 1. So our soil parameters are given here, very similar to the previous example. And we've worked out the active pressure and the passive pressure using the Coulomb equations. So they work as 0.36.1. So the seismic parameters, so we're looking at a relatively short return period. So we're looking at a topographic amplification of 1 and a wall displacement factor of 0.3. So our KH works out as a tiny 0.034 G. And that MO equation, as it's called, I've split it up into 2. So we've got this parameter D, which takes into account the parameter theta, which is looking at the horizontal acceleration due to the earthquake. And we shove that D into the denominator of the equation for active earth pressure, KAE, in the earthquake case. So here are the seismic parameters for the wall. So we're looking at a return period of 0.5. And near fault again as 1. So we're looking at ductility here as 1 and our period is 0.4. And therefore our seismic coefficient is a mere 0.21. So our wall loading, we work out long-term, short-term and earthquake loading. You're going to take account of the weight of the wall above the ground. So the weight of the wall actually imposes an earthquake load on your retaining wall now. So the seismic load of the wall, I know it's not a lot, but it counts. It's 1.36 kilonewtons per meter. We've got our wind load and we've got our long-term and short-term earthquake loads. So from that, we get our bending. So our moments, looking at long term, you just take those forces that you've worked out above, some due to the soil, some due to the surcharge, and multiply it by the angle required, and you get a 1.78 kilonewton meters of moment. Looking at the short term, you've got slightly different parameters, and that works out as 2. Similarly with the earthquake, you're using the KA for the earthquake with a factor and it works out as 1.31. We also look at the wind on the wall and the EQ bending because of the wall. So that gives a design moment of 5.4 and a design shear of 6.8 kilonewtons. So then we actually come to design the wall in terms of the concrete section. So some basic parameters. Our wall is 150 millimeters thick. We're taking a unit length of it, and we're having a guess of what the reinforcement will be. So let's have a guess at HD12s at 300 for the vertical bars. The laces or the anti-crackers are also HD12s, but this time at 400. So from that, you can work out what your steel areas are. And from that, you can work out what your flexural capacity is based on the equations given in NZS 3101. You use the standard stress block given in 3101, and your moment capacity works out as 11.1. So therefore, your utilization factor is 49%. So we're good to go on bending. In terms of shear, NZ3101 gives you a whole series of equations to work out what the shear capacity is, depending on how thick and how strong your concrete is. It pops out that your VC, your basic concrete shear strength, works out as 0.25. The shear resisted by the concrete, therefore, is 18.7. Shear resisted by the stirrup, in this case our vertical bars, is 26 kilonewtons. We're putting on a reduction factor of 0.75 because looking at shear, and we have a design shear capacity of 33.6. And again, our utilization factor is 20%. So shear doesn't usually dominate the design of these concrete walls. Then we get back to some geotechnics, and we're looking at the footing design. So we've worked out what the loading is on the footing, a long-term, short-term, and earthquake, and that's the 7.9, 8.6, and 5.2. And all we're doing here is multiplying the forces by their lever arms again. And again, we use this differentiation between the earthquake loads and the static loads to work out the difference. Also got our wind on the wall and the loading due to seismic effects on the wall. And that works out, take the moments, we've got a long-term moment of 3.5 and a short-term moment of 4.8. We've also got the wind on the wall and the EQ of the wall. So our design moment is we take the maximums of these parameters for the cases that can coexist, in which case our design moment works out as 7.73 and a design shear works out as 9.7. So not all of the moments can exist at once. So we look at the stability of the footing. Again, working out what the load, dead load of the wall and the dead load of the footing. So these are going to be our restoring moments. What are our lever arms? And our total restoring moment works out as 16.2. The distance to the reaction works out as 0.41. That's merely the moment divided by the reaction. So our bearing length is 0.82. That gives us a bearing pressure of 25.12 kPa. So let's check the bearing capacity. And again, we're looking at soil parameters that we've seen before. We look at the effective stress at the foundation. That's a 5.1 because of the depth. We've got a bearing factor, again, taken from B1 VM4. So our NQ, NC, and N gamma calculated. We've taken our shape factors all as 1 because we're looking at a long strip foundation in this case. We're looking at horizontal ground, so our ground inclination factors are 1. We've got depth factors calculated and our load inclination factors worked out from the loading above, which gives us an ultimate bearing strength of 234 and a design bearing strength is 117. So our bearing strength utilization is 21% based on that. So we're okay with that. Looking at the concrete footing, so we put in similar parameters from above. We've got our concrete strengths and we're working out the concrete footing sizes. So we've got a thickness of 300 and a width, looking at unit width and gross area of the concrete. Again, we're looking at HD12s, calling it vertical reinforcement. The vertical reinforcement continues down into the footing. And so we've got our steel areas calculated from that. And from that, using the equations in NZS 3101, we can work out what the moment capacity is. In this case, the moment capacity of the footing is 32.5. Yet the applied moment is 12, worked out from above. So our utilization is 37%. Again, looking at the shear capacity of the footing, we work out the concrete shear capacity is 0.44. And the shear resistance provided by the stirrups, in this case the bars, is 73, which gives us a shear capacity of 123 kilonewtons. And that gives us a utilization of 17%. So that is the end of that seminar. Our next seminar will be possibly in the new year on a subject to be announced. So all suggestions will be considered.